Hello everyone, welcome back. So yesterday night we we solved or at least thought about the approach for the first 20 problems in the list of problems which appeared more frequently in meta interviews in the past 30 days. So yeah, the general uh, order that we followed was basically okay. Let me close the unwanted tabs here. Okay, here we came to the meta or the Facebook list, and then we filtered out the questions that has appeared in the past 30 days, and then we sorted it by frequency, and then we solved the first 20 problems or looked into the approach of that, either of those. Let's continue with the same series. So I think if we cover like 35 to 40, that should be good enough, or I'll see if I can continue with that based on how much time it takes in this session to solve the problems. Let's go faster so that okay, so that we can cover more problems today. Let's move to the first problem for today. LeetCode 129 sum root to leaf numbers. You are given the root of a binary tree containing digits 0 to 9. Okay. Each root to leaf path in the tree represents a number. For example, the root to leaf path 1, 2, 3 represents the number 1, 2, 3. Okay. Return the total sum of all root to leaf numbers. Test cases are generated so that the number will fit in 32-bit integer. A leaf node is a node with no children. Okay, I think I understood the problem. So here, for example, in this tree, in this given tree, this is 1, 2 is 12, 1, 3 is 13, 12 plus 13 is 25. So that is what we need to output. And here 495 plus 491 plus 40. 495 plus 491. So it is 9 plus 5, 14. So 986 plus 40. So 1086. Sorry, so 1026. So that's what the output is. How to approach this problem? So here, as the problem states, we need to traverse somehow from the root node to the other nodes, and we keep iterating until the leaf or the null node basically, and then we encounter the leaf. We will return the entire value of the path until then, and then we keep floating it up to the path, and then we make it as add it as a sum. I think that sounds good. Like for every in the every path in every each and every node, I will be returning the sum of the path traversed by the left node and the right node, and then add it and bubble it up. But I won't use it. I'll bubble up the numbers till now, or the total path till now. Let's see how we have solved this one. All path sum and sum of numbers. If root is null, then we will just return 0, nothing. And then al path sum is equal to 0. Okay, we just initialized it. And then pre-order traversal. Pre-order traversal is pre means current, left, right, pre-order traversal. So current path sum is equal to current path sum star 100 star 10 plus node value. Okay, so okay, I'm just getting the value, like trying to create a number out of these single digits. So 1 and then 2. So how to compute this one? So when we come to 1, like our current path sum is 0. So 0 star 10, 0 plus 1, 1 the value will be. And then when I come to this leaf node, so current path sum was 1. So 1 star 10 is 10, and then plus 2 in the in position, that will make it 12, and in the same way this will make it 13, and then we will be returning 15 here. Okay, so al path sum plus or is equal to current path sum. Okay, current path sum is calculated by this formula, and then if node dot left is equal to null and node dot right is equal to null, then al path sum plus or is equal to current path sum. Okay, if node dot left, if both of them are null, if left and right both are null, okay, then I'm just adding it to the al path sum. So whenever I'm reaching the leaf node, I'm adding it to the all path sum. Basically, I know that it's like the left node of the 2 is null and right node of the 2 is null. So what did I computed until now? The all path sum was 12. So I'll just add it to the all path sum. The current path sum is 12. I'll add it to the all path sum, which is 0. So it became 12. And then when I reach this leaf node, left is null, right is null, and then the current path sum is 13, and then I add it to the al path sum, which was 12. 12 plus 13 makes it 25. So yeah, this is a clean approach. We can execute it and see. It is a O of n approach because we are traversing each and every node only once, and space is O of n as well. Since we are keeping a we are calling it recursively and keeping a stack of in the stack memory, we are keeping all the nodes in the worst case. So let's execute this one. Okay, this looks like a good approach. Only intuition is, okay, we cannot pass the al path sum into this one. We can just compute the current path sum. When we come to the leaf, we will add the current path sum to the al path sum. So we reach the node here, or the leaf node here, which is 2. And then we just added the current path sum to the al path sum. Current path sum was 0, or al path sum was 0, so the current path sum was 12. I just added it, so al path sum became 12. And then when I reached this leaf node, the current path sum was 13, and then I added it to the al path sum, which was 12. 12 plus 13, it made it 25, and then I just returned 25. And yeah, that makes it. That is good. Okay. So this is the base case. Whenever I reach the leaf node, I'm just appending the value to the al path sum. Okay, there is another approach using BFS. Let's look into that approach as well. It might not necessarily help in solving this problem. Nobody might ask solve with this approach or anything, but knowing the approach would give us the ability to solve some other similar problems. That's why I look into the alternative approaches as well, even though we arrive at a solution. So in this one, Q is equal to, like I'm using BFS and time and space complexity is the same. Initiating the queue to traverse using breadth first search approach, I think. Breadth first search approach. And then Q dot add root. I added the root. And then node value is equal to new hash map. Node value is equal to new hash map. Okay. Node value dot put root dot root value. Okay. In the root, whatever the value is, root dot value. Int al path sum is equal to 0. While q is not empty, current node is equal to q dot poll. Int current value is equal to node value dot get current node. If current node dot left is equal to null, and if current node dot right is equal to null, same logic. Basically, we are doing it in a iterative approach instead of recursive approach. If this means we reach the leaf node. So if we have reached the leaf node, which doesn't have a left node or a right node, then we are adding the current value of that node or current value of that path into the al path sum. Else, what I'm doing is, if current node dot left is not equal to null, then I need to add the left into the queue. And then also, if the right is not null, then I'm adding the right node into the queue. And then also I'm putting the node value into current node, like node value into the hash map that we created by keeping the path until then, like current value star 10 plus current node dot right dot value. So basically the same number conversion from a single digits, like, okay, it was 1 star 10, 0 star 10 plus 1, that became 1. And then 1 star 10 plus 2 became 12. 1 star 10 plus 3 became 13. Here in this example, it was 0. 0 star 10 plus 4, 4. And 4 star 10 plus 0, 40. here in this on this side, 4 star 10 plus 9, 49. So 49 star 10 plus 5, 495. 49 star 10 plus 1, 491. 495 plus 491 plus 40, it makes it 1026. So that's how we have been computing. If we executed it, it would be almost similar. We have just done it in like iterative and recursive approach. We have used a lot more data structures here as compared to the previous approach. Okay, let's stick to the pre-order approach, which is easier here. Okay, let's move on to the next problem now. Moving average from data stream. Moving average from data stream. Okay, this is LeetCode number 346, moving average from data stream. It's a LeetCode easy problem. Given a stream of integers and a window size, calculate the moving average of all the integers in the sliding window. Implement the moving average class. Moving average in size initializes the object with the size of the window size and double returns the moving average of the last window of the last size values of the stream. Okay. Implement the moving average class, and then moving average method initializes the object with size of the window size. Okay. So we have constructor with the value for size that initializes the window size of the window, and then double next returns the moving average of the last size values of the string. Double next returns the moving average of the last size values of the string. Okay, so let's look at an example. Moving average, and we initialize the size as 3, and the next of 1 gave us 1 dot, we just returned 1, and next of 10, so that returned last 3 averages, like okay, 10 plus 1, 11, 11 by 2, 5.5, and then again next, that made it like 10 plus 1, 11, 11 plus 3, 14, 14 divided by 3, it is 4.667, and then again next, so that then we added 5, so 5 plus 3, 8, 8 plus 10, 8, 18, 18 divided by 3, we are calculating the maximum window size is 3, so that makes it 18 by 3 is 6, that returns 6. Moving average, okay, so the window size, okay, so we will just keep the window size. So we have a queue here, in size is equal to, in the queue we know that first in first out, it follows the rule FIFO, or first in first out. So whatever we inserted first, basically in the next method we inserted this 1, that gets out when the size of the queue becomes greater than whatever the size of the window given, and we do not care about the older values anyway for these two methods, so we don't have to keep that, we can discard that from the queue. So moving average initialized to size, q is equal to linked list, I initialized it, and this dot size is size, and this dot total is 0. We are computing a running total as well in order to make the computation easy. And then next value, whenever they call the next method with a value, the total would become this dot total is equal to total plus value, that is evident. So can use the shorthand for that, total plus value, this dot q dot add value. Okay, I'm adding that new value to the queue, and then if the queue dot size is greater than size, then I'm just removing it from the queue, this dot queue dot remove, and then at the same time this dot total, I need to reduce it from the total as well. So total is equal to total minus removed value. Okay, total minus removed value, and then I need to return the average of that. So return this dot total divided by double of size. So here okay, we are just returning it here. I have added it in the comment. So if I just call the q.size method, that means we are computing it again. And q.size is usually it's the size that we have initialized to. Like if it is greater than the size, that means we have the size here. Otherwise, we are just using the size that we had before. So yeah, otherwise we need to compute the total size. Like if it is less than size, let's say the size was given as 100 and the queue size is currently like only we have added 85 elements, then we have to divide it by 85. So we are looking at, we have to compute 85. But if we know that, okay, it went past 100, like if the size became 101, then only we reduce it back to 100. Then we can just divide it by 100, which we already initialized it with. So that's okay. But irrespective, even if we don't have this method, it should work the same way. Yeah. Yeah, it would work. So if we add this one, that should work too. Okay. For the code readability, let's leave it this way. Got it. Let's move on to the next problem now. Top k frequent elements. Did we solve all the problems above? Yes. Okay. Top k frequent elements. Given an integer array nums and an integer k, return the top k frequent elements. You may return the answer in any order. It's a LeetCode medium problem, LeetCode 347, and nums are given as 1, 1, 1, 2, 2, 3, k is equal to 2. Top k frequent elements, okay, 1 and 2. 1 appeared 3 times and 2 appeared twice. So I have solved this problem elaborately in another video, but yeah, when I explained the priority queue. But I think the logic is simple here. So we can create a hash map with the frequency, a hash map of number with the frequency. So in the map, I have shown this in the visualization here. So 1 has appeared 3 times. 1 is the number and 3 is its frequency. 2 has appeared 2 times. So 2 is the number and 2 is its frequency. 3 has appeared once. 3 has appeared once. And this one, I think I gave another example. That's when I just computed this. Okay, min heap of size k or min heap of size 2. So this should only contain these two elements. Size, min heap of size 2, and the size is based on the frequency, not based on the number. So we will have these two elements there. Since it is based on the frequency, we will arrange it based on the frequency. Let's initialize the hash map here. Map num frequency map, we created a hash map. It is integer to integer. And then we arrange the num frequency map based on the order of the frequency. Okay, num frequency dot put, if the number already exists, then just increment it. If the number does not exist, then assign a default value as 0 and then increment it by 1. So now we will have this map ready to go for this input. After doing that, let's initialize a priority queue or a min heap. Why min heap? Because we need to calculate the top k frequent elements. So when I compare with the top element, I should know whether I am eligible to get into the heap or not. I mean, an element when it is compared to the top or the peak of the queue, I should know. If I if I have a max heap, let's say, then whenever I compare with the peak, like if I just add the first element itself as the largest element in the array, then there is no room to add any more elements into that array or any more element into that peak, because none of the elements would be greater than that. That's why what we do is we create a min heap where we will try to retain the top k elements there, starting from minimum to maximum in that min heap. So min heap is the natural ordering here. Min heap is the natural ordering in Java. If we have to make it as a max heap, then we have to reverse the direction of the sorting that we need to perform. But here the challenging part for us is we need to order it based on the frequency, not based on the value of the number. So in the priority queue of type frequency pair, how I have defined it, I have created a custom class here, frequency pair, num and frequency. All I can do is I can just do integer array as well instead of frequency pair. I'll show that if there is time. And then new priority queue, and then I have added element 1 and element 2, which is of type frequency pair, and then I'm comparing the frequency of both the elements and sorting the priority queue based on that, not based on the value but based on the frequency. There is a num as well. I'm not comparing based on the num, I'm comparing based on the frequency. And then what I'll do, I'll add all the elements in the hash map into the min heap. Okay, I'm iterating through the hash map, each key by iterating through the key set, and I'm adding that to min heap. Min heap dot add new frequency pair of key comma num frequency map dot get. This is the frequency, this is the value. And then if the min heap size exceeds k, then I'm polling it out of the min heap dot poll. So that makes the logic o log k instead of o log n, because in the min heap, for every operation it takes log k, because the size of the min heap is at like we are keeping it at k, so it would be log k. What if we had added all the elements into the heap, then it would have been O of log n operation for each of the pole, and for n elements it would be n log n. So we reduced it to O of log k, so for n operations it would be n log k. And then we care only about that. Since we care only about the top k elements, we don't have to retain the other values. And the output is in the format of integer array. We are converting that min heap elements into the integer array top k elements, and then as long as the min heap is not empty, I'm just adding it to I'm pulling it from the min heap and adding it to the top k elements. And order does not matter, so I'm returning from the increasing sorted order, because since it is min heap, it will keep returning the value with minimum frequency. So I'm adding the values from minimum frequency to maximum frequency. So in my case, if we see here, okay, here it came as expected output is 1 2, but I'm returning it as 2 1 because I'm going from minimum frequency to maximum frequency. As I said in min heap, minimum frequency is 2 appear 2 times and 1 appear 3 times. So 2 comes first and then 1 comes later. But it doesn't matter. In the question they have the constraint. They have mentioned explicitly that you may return the answer in any order. So we are good to go. Okay, and then to make it simple, if we do not want to create any custom class or anything, let's say if that is the case, then we can just simply write it as integer array, and then element 1 and element 2, let's make it as element 1 of 1, where the 0th element is the value and the first element is the frequency. So we are comparing the first element here, and then here instead of new frequency pair, what we will do is min heap dot add new integer array, and I'll add these two values. Okay, that makes it perfect. So let's run it. Okay, when I do min heap dot poll, I need to return the value of it by 0. Okay, it works. And since I used a structure provided by the language, it became faster. So yeah, so this should be good for this problem, top k frequent elements. Let's move on to the next one. LRU cache. Okay, we have seen it so many times. how many problems did we go through today? I think 3. Let's do LRU cache. Design a data structure that follows the constraint of least recently used cache or LRU cache. Implement the LRU cache class. LRU cache int capacity. Okay, there is a constructor initializes the LRU cache with positive size capacity, and there is a get method returns the value the key if it exists, otherwise returns -1, and there is a put method update the value of the key if the key exists, otherwise add the key value paired to the cache. If the number of key exceeds capacity from this operation, evict the least recently used key. Okay, they have given the entire requirement, like basically explaining like operation by operation. We need to exactly follow the steps that they have provided. The function get and put must each run in O of 1 average time complexity. Okay, got it. So, and I think this list node is provided by them or not. I'm not very sure about it. Okay, let us create a list node this way. So this is a like doubly linked list node. So doubly linked list node where we are creating key comma value for every element, and then I have a next pointer or the reference to the next element, and I have a pointer or a reference to the previous element. So this is basically a node of a doubly linked list. So using a doubly linked list and a hash map. Okay, and then class LRU cache, I'm initializing, I need a capacity, and then I need a head, I need a tail, and then I need a map as well, map of integer, I mean the value to that list node. So whenever I'm initializing with the capacity, I assign that capacity to the corresponding variable, and head I created a dummy node, new list node of -1, -1, and tail I have created a dummy node. And then this dot head dot next, I have connected the head to the tail, this dot tail, and then tail dot previous becomes head, and I initialize the cache to the cache as new hash map. And then when I'm trying to get a method, if this dot cache dot contains key, if this dot cache doesn't contain key, then return -1. And like basically if the cache itself doesn't contain that key, then we don't have to do anything at all. We don't have to change any order or anything. We just return -1 and do nothing. If that contains, if the cache contains the key, then what we need to do is, okay, then the node to be returned is this dot cache dot get. So that would point us to the right node, and then we need to call the method remove node. Once we return that, like once we figure out which value to be returned, why we are removing it, basically it might be anywhere in the doubly linked list, but what we need to do is we need to add it to the front because it is the most recently used element and least likely to get evicted. That's why we will just get the value of that node and then remove it from its current position and then add it to the front of the node. So remove node will be remove node, and then we pass the pointer for that node or the reference for that node, and then add to front. I'll pass the reference for that node again, and then return whatever the value that we needed to be returned. So this would be O of 1 operation. How in a linked list, basically removing the node is just like and we have the node's reference, we have the previous and the next pointer. So if I have to remove a particular node, what I'll do is I'll just connect the previous node to its next node, and then I'll mark the next node's previous node as current node's previous node, and then this will be removed or dereferenced. And then add to the front. Add to the front means basically I'll add this particular node as next node of the head, and then the current next node of the head would become the next node of this node, and then the previous also I'll assign it in the same way. So let's look into the remove node method implementation here. It will be simple. Whenever I want to remove the node and I have the reference for that node.previous.next. So its previous node's next will be node's next, and node.next.previous. Its next node's previous value will be the current node's previous. So node.previous. So this will be like removing the node or dereferencing the node, and then add to the front method and give a node. So how to implement this one, add to the front? Okay, so list node, I have been given the node, next node is equal to head.next. Whatever the next node is to the head.next, I'm capturing it in one of the reference. So head.next will become the node that I want to add to the front. Head.next will be that node, and node.previous will be head. So I have connections established with the head node, and then I need to establish the connection with the next node as well. So node.next node, current node's next node will be next node, and the next node's previous node will be, it was head before, but what I'll do is next node's previous node will be current node. That completes the logic for this getter method. And then let's look into the put method here. All of this happens in O of 1. In the put method, what I'm checking is if the cache contains the key, then node to be removed is equal to, then I know that if the cache contains the key. Okay, if the cache already contains the key, then basically I need to override the key or override the method. So how do I override it? If the cache is contained in the key, already there is a value associated with it. What I'll do is I'll remove this whatever the value associated with it, and then I'll add it with a new value. And then also once I add a new value, what I need to do, this is the most recently used key value pair, right? So I need to add it to the front. So basically whatever the existing node was there before, so I will have to remove that node. So that's what I'm doing here. If the cache contains the key, then the node to be removed is cache.get that, and then remove the node. Remove the node is basically the same thing, dereferencing logic that we followed in the getter method. And then once we remove the node, I need to add it to the cache again. So node to be added is new list node. Okay, I created a new node with the key and new key and the value that is provided, and then add it to the front. Because this is the most recently used one, I'll be adding it to the front of the linked list. Add to the front, node to be added. And then what I need to do, this dot cache dot put. So I'm adding it to the cache as well. I mean, cache already had this value, but it had it with a different node. So I'm overriding it. This dot cache dot put, this is the key, whatever, and then the value will be the new node that we created instead of the old node that we already removed or dereferenced. So this will override it. And then at that point, we will check if the size of the cache, like if this one did not satisfy, like if this one satisfied, then basically we didn't have to do this one. If we didn't have to follow this step. But if the cache did not contain the key, if we are adding a new key and if that exceeds the size of the cache, then what we do is if this cache dot size is greater than the capacity, then we need to just remove one node from the end of the list. So I'm just calling node to be removed is removed last, and then I'm removing the same node also from the cache also, cache dot remove node to be removed dot key. So how I'm implementing remove last. Remove last is basically removing the previous node of the tail or removing the previous node of the dummy tail. So remove last is to be deleted tail dot previous. To be deleted is tail dot previous, and then tail dot previous is equal to be deleted dot previous. Okay, or else what we can do is we know that node that has to be deleted, and then we can just call the remove node method instead of doing all this. Remove node to be deleted, and we can just return to be deleted. This should work too as far as I know. Yeah. Okay, we got the pointer of the to be deleted, and also already we have implemented the remove node method. So we are just calling that method, remove the to be deleted method, and then returning that particular node which was deleted, and then removing that key from the cache as well, since we deleted that value from the doubly linked list. So that is a good approach, using a list node that we ourselves has created. There are other approaches to solve this problem using a here using a built-in linked hash map. In Java language itself, there is a built-in linked hash map we can use that one as well. Linked hash map means it is a combination of linked list and a hash map both. So I'm creating a cache of type linked hash map, and then capacity is the same thing. And I'm initializing that cache as a new linked hash map, and capacity, I'm initializing it as capacity. And then for the getter method, I'm doing this exactly the same thing that I had done before. If the cache does not contains the key, then I'm just returning -1. If the cache contains the key, then int value is equal to this.cache.get. Okay, this.cache.get, and then this.cache.put first. Put first is the method I'm using here. Okay, key comma value. I'm adding the key and the value here, and adding it as the first element, and then return the value. Okay, whatever the value here, let me think a little bit. Okay, value that has to be returned is value this.cache.get of key, and this.cache.put first key comma value. Okay, so whatever the value I need to return, I identified it, and then I'm just adding that key value pair into the first position, and then I'm returning the value. Basically, it's like there I removed and added it to the front. Here I have put front that would override and move the position of that node to the first beginning. And then in the put method, if the cache contains the key, then I'm just removing it because I need to add it to the first position, and also I need to override the value into the current value that is being passed. Else if the cache does not contains the key, then I'm checking if the cache.size is equal to capacity. Then I'm just polling the last entry. I'm removing one of the entry if the cache does not contain the key, and then I'm adding the element to the beginning of the cache, adding the key value to the beginning of the cache. So irrespective if it contains or not, if the cache contains the key or not, I need to call this method this.cache.put first for that key and value. But based on whether it contains or not, that size matters. Like if the same key were already contained in the map, that means there would be no change to the size. Then I don't have to poll the last entry. Then I just have to remove that key, and then I'm adding that key back here, so size wouldn't change. Otherwise, if the key was not contained in the cache, then I'm checking if the cache size became equal to the capacity. If that is the case, I know that if it is equal to the capacity now, I know that I'm going to add one more key value that would exceed the capacity. That's why I'm making space for that by polling the last entry. Cache.poll the last entry and then put first. So this will put first means this will add it to the beginning. So since this is the most recent element that is being accessed in the cache. Let's run this one as well. Okay, so this makes sense. Let's take a small break and then get back to the series again. Let's read the messages. Okay, Shaker, I see that you have joined again. Thank you for joining, and yeah, it's great. Feel free to ask me any question that you have. I'm back with the same thing. Like I had some, I was busy with certain things, and also I had some health issues, so I had stopped streaming for a while. Not for long, I guess. It was like I think it's been almost 15 days or couple of weeks since I streamed, and I'm starting to get regular now. I need to keep it going. I feel good about learning new things and also sharing my learning as well. So it's awesome. Welcome back, and keep me posted about any questions that you have or any approaches that I need to change. Let's take a break now. Okay, let's move to the next problem now. So what's happening here? Okay, so we just did LRU cache, and then now dot product of two sparse vectors. I have no idea about this one, I think. Okay, given two sparse vectors, compute their dot product. Implement the class sparse vector. Okay, and then the constructor initializes the object with the vector nums. Okay, and then dot product of vector, compute the dot product between the instance of the sparse vector and the vector. Okay, they're passing another vector instance. Okay, a sparse vector is a vector that has mostly zero values. You should store the sparse vector efficiently and compute the dot product between two sparse vectors. Follow what if only one of the vectors is sparse. Okay, so num1 10023 dot product is basically okay, both of those. v1 is equal to sparse vector of nums of 0, v1 is equal to sparse vector of nums of 1, and v2 is equal to sparse vector of nums of 2. Okay, v1 dot product of v2 is equal to 1 star 0 plus 0 star 3 plus 0 star 0. Okay, got it. So what they are doing is okay, whenever we are initializing the sparse vector, I'm initializing since I know that most of them are values with 0, I don't have to maintain those values, but I can just maintain the values of the values that are present. And also what matters is dot product means it's like I'm multiplying the corresponding element in the same index in the other vector. So 1 star 0, 0 star 3, 0 star 0, like that. So so the index is important as well. So I'll store the value at any index if it's a non-zero value. That's what I'll do. So index with values, and then whenever an integer nums is given, index with values, I'm iterating through the nums array. Int I is equal to 0. Okay, if nums of I not equal to 0, if the number is not equal to 0, then I'm just adding it to the index with values map. Index with values dot put I comma nums of I, and this is the instance variable in that class accessible from anywhere. And then here I need to multiply it with another vector. Return the dot product of the two sparse vectors they are asking. And what I'm doing is I'm iterating through the map index with values now. Like rather than iterating through this numbers which had mostly 0, I'm iterating through the map, all of whose values matters. Those are non-zero values. So I have the entry here. So these days I'm like I find it difficult to remember the syntax of like map dot entry of something. All I do is basically if I know the format of the key or the type of the key, which is integer, I'll just do integer key and then I'll iterate through the key set, and then if I know the key I can get the value from that map of 1, so it wouldn't hurt as well. But yeah, here I have the value vector dot index with values dot contains key. If the past vector also contains the key that is being iterated on as of now, then product is equal to product plus is equal to entry dot get value star vector dot get index with value dot get. Okay, so whatever the value is here, I'm multiplying with the value in the vector also for the corresponding index. So yeah, this makes sense. And then I'm returning the product of that one. So that is sparse matrix. So all I care about is the index and the value, and I'm just multiplying the corresponding values in the I'm multiplying the values in the corresponding indexes in both the vectors. That should be good. Let's run this one again. Okay. Now next one is binary tree right side view. Okay. This is LeetCode 199 binary tree right side view. It's a LeetCode medium problem. Given the root of a binary tree, imagine yourself standing on the right side of it. Okay. Return the values of the nodes you can see ordered from top to bottom. So in this tree, for example, okay, 1, 2, 3, sorry, 1, 3, 4 are the elements that are visible from the right side. So that should be the output. And in this tree, 1, 3, and then also, even though these are on the left side, but there are no elements on the right side. This is the rightmost node in that particular level. That is the key. So in this level, this is the rightmost element. In this level, this is the rightmost element. This level, this is the rightmost element. So the output here is 1, 3, 4, 5. 1, 3, 4, 5 is the output here. Okay. Yeah, this makes sense now. After looking at this example, it's pretty clear that we need to do level order traversal and then capture only the last element in the output. So that's what I'm going to do. So in order to do level order traversal, I usually prefer a DFS or a breadth first search. Sorry, BFS or a breadth first search using a queue. But here, let's see, this is another approach here. Capture the right side view. This is the method given, and I'm given a root as well. I have the right side view. I have created a kind of result type, and then if the root is null, just return the empty list. If not, I'm passing the right side view array, the output, and then the current node, and also 0 is, I think, the level. Yeah, 0 is the level. So if right side nodes dot size is equal to level, okay, right side nodes dot size is equal to level, then right side nodes dot add node dot value. Okay, what are they doing here? So here they are comparing right side nodes dot size. Right side node dot size, when I enter this one, it is 0. It is equal to level. Yeah, that is equal to level. Right side node dot add node dot value. So I'll add the value of the root node. And then if the node dot right not equal to null, then capture, I'm just calling this method, capture right node dot right, level plus 1, right side nodes. Okay, the same thing I'm just passing. And then if the node dot left not equal to null, capture right node dot left, level plus 1, right side nodes. Okay, so first I'm capturing the right node and then I'm capturing the left node. So what this one would do, so okay, I came here to the node 3 and then I did the same thing. Okay, right side node dot size is 1 now, since I had added this one. And is it equal to level? Yes, level is also 1 now. So I will add the value here, 1, 3 to the right side nodes. And then if node dot right not equal to null, so node dot right is null and node dot left is also null. So basically I won't do anything and then we'll return, and the initial method from the one node. So I'm done with the traversal of the right side now. So I need to traverse the left side. If the left is not null, then capture right node of node dot left, capture right node of this one, and level also I have marked it as 3. So basically level as from 0 to 1, and I came to this node, and here node dot right is null, and node dot size, right side nodes dot size is not equal to level. Level is 1 and node size is 2. Level is 1 but node size is 2, so I won't add it to the output. And the node dot right is also null of this. node 2. So I won't perform this one. Node.left is not equal to null. So what I'll do, I'll call the capture right node of this node. I'll pass this node, and level would become level plus 1, which is 0, 1, 2. So level will become 2. And then if the okay, I'm checking here, if right side node dot size is equal to level, then I'm adding it to the node dot value. Okay, the size of this one is equal to level, so size of this one is 2, and then level is 2 now. So I'm just adding the right side nodes, the current value. So I'm adding 4, 1, 3, and 4 I have added. And then again, node dot right is null. I'm just okay. Basically, the intuition behind this approach is, what we are doing here is, if we are checking the size of the result or the output here, if that is equal to the level, then I'm adding the current node to the result. Otherwise, I'm just iterating through. So why this matters? So basically, in each level, I can insert only one element, and I want to insert the rightmost element in each level. So that is the reason, like, I'm checking if the size is equal to level, then I'm adding another element. If size is already greater than that level, then that means I have already added one element in that level, so I didn't add this element. And I came here, and how do I know this is the rightmost element in that level? Because I'm traversing from the right first. Like, I'm not doing node.left not equal to null. Usually we traverse from current left right. Here we have changed the direction. We are traversing from the right node first. So if at all there was a right node existed, then I would have traversed that first. Since the right node did not exist, then I came to the left node. If the right node existed for this 3 itself, then I would have already traversed and added it to the output. So, and the output size would have been greater than the level. Then there was no chance to add this value. Since none of these had rightmost childs, so I'm ending up adding this left node itself into the array. So this makes it clear. But to come up with that approach during the interview, I'm not sure if I can do it. Depends on the day, probably. But this approach, the level order traversal, this is a common thing that I have solved or looked into many times. In the level order traversal, basically I traverse the tree level by level. So 1, and then 2, 3, and then 4, whatever elements would be in this level. And then I'll get the last element in that array, and I'll add it to the output. So it's as simple as that. So let's look into that approach also. Let's submit this one. Okay, nice. That's 100% output. Let's comment out that. But this one is also O of n and O of d space. So there's no harm in that, but it is like additional logic than what is exactly required to capture the right side view. Like, we are capturing more information than it is required. So here, so how do I do usually the level order traversal? I come from the current level. For the current level, I have kept an array, and then right side view. Okay, right side view is the output. If root is null, then I'm just returning the empty list. Otherwise, I'm traversing current level is okay, new linked list, and next level is new linked list. I'm adding the root to the current level, and then as long as the current level is not empty, I keep traversing. If the current level dot size is equal to 1, then right side view dot add current level dot peak dot val. Okay. So basically, I'm kind of trying to add the first element here also. If the current level dot size is 1, then I'm adding that to the current level dot peak dot value. I'm adding that to the right side view. Why when the size is 1? So why when the size is 1? Because that would be the first node that I'm traversing. Why that would be the first one? Because here I'm going through left first, but it is a stack. I'm adding the left node first, and then I'm adding the right node. So the right node will be piled up above the left node in the stack. And then when I try to take out that node and try to execute, so that would be the first node in that level. So current level dot size is equal to 1. Oh, but it is a queue, not a stack. Sorry, forget whatever I mentioned. So here what I'm saying is, in the current level, when the size is 1, that means that's the last element, and it's a queue. I'm adding it like from left to right. Left to right means that the rightmost element in that level would be the last element. So when one element is remaining, that means that's the rightmost element in that level. Then I'm adding it to the right side view, which is the result in this case. Yeah, and usual level order traversal, I'm traversing like I want to traverse the left node, so I'm adding left level dot add node dot left, and then I want to traverse to the right node, next level dot add, I'm adding it to the next level. And when the current level becomes empty, then the current level becomes like I'm replacing the current level by the next level queue, and also I'm instantiating the next level by a fresh new linked list here. And then I'll follow the same process. Current level is not empty again, and it will keep iterating, and it will add the subsequent children of the next level here. So let's run this one as well and see. Are there any optimizations that we can perform in this one? So if it was a balanced binary tree, then we could have reduced it to using one data structure instead of two here. Or else we can use something like a delimiter for adding the next level elements instead of all we can do is we can just add a null element or a -1 as a or a dummy tree node element as a delimiter here. So let's see how. Let me copy the same code and let me run it here. Okay, and then here, if the right side view and next level, instead of next level, in the current level, I'll add a current level dot add null. I have added a null element after the root, and then if current level dot size, okay, instead of this, okay, this one let's keep doing this one, and then if current level let's check here. If current level dot peak is equal to null, then what I'll do is current level dot add null at the end. Okay, and also I'll poll the current level dot poll, and just remove the current null and then add it to the end of that level. And through that, I don't need any other level separated data structure here. I don't need next level. Yeah, this should do. Let's see. Okay, instead of 1, let's make it as 2. Because 1 would be the dummy element there. It's null, okay. So what did I do here? Okay, current level. For the current level, I have added a root node and then a null. And then I came here. If current level is not empty, I pulled the current level. And then if current level dot size is 2, then I have added to the right side view. Okay. And then I have taken the node which is pulled the current level. So first in, first out. First in was root, so that would be the first out. Node dot left not equal to null. Okay, I added the node dot left to the current level, and node dot right not equal to null. I added that to the node dot right, and current level dot peak is equal to null. Yes, it is null. Then I'm just current level dot peak is null. I'm pulling that out, and current level dot add null. Adding it to the end of the current level. Okay, and then I have come here. If the current level dot size is equal to 2, current level dot size is not equal to 2, it's equal to 3 as of now. So I won't add it, and then I'll try to handle the left side case, which is 2. If node dot left not equal to null, then I'm adding, okay, and I'm adding its right as well. Okay, for some reason it looks good to me. There might be a small or a minute error. How did the node itself become null? Whenever the current level is null, I'm removing it and adding it. Okay, if it's the final one, then I should not add it. If current level dot peak is equal to null, and current, and if there are other elements, current level dot size. Okay, this one I'll add here. If there are still more elements left, if current level dot, if it is not empty, then only I'll append it, because there is more traversal to do. If it is empty, then I don't have to do more traversals, so I won't do anything. Why I did exactly this one is, so this might be the last element, last null element that is failing to do null dot left, basically, that is throwing an error. So instead of adding null at the last element as well, I'm checking if after polling the null element, if there are no more elements left, then I don't have to append it with the null at the end. So I'm checking if the current level is empty, then only is not empty, then only I'm appending it with the null. If the current element has any element, then I'm appending. Okay, makes sense. Let's see. 1, 3, 4, and my output is 1 and 4. Okay, when I came to 2 here, I cannot check for the size 2 because I already added the children of 2, which is 5, into the map, and then yeah, I cannot check for this one. So what I can do is, if the current level dot peak is null, then I will just add the right side view. Yeah, so this one works. So I just remove the necessity to have another queue here just by adding a delimiter as null. And also in this case, okay, so I commented this one out and uncomment this original approach using 2 queues. In this case also, I think if size is equal to 1, then let's do this. Why am I writing all this? So this should be node dot value. Okay, current level dot size is 0 when it our current level dot is empty. Current level dot is empty. I'm checking that anyway here, so I can follow the same pattern like we followed in the last method. And instead of current level dot p, just do it as node dot value. Okay, submitted. So this one works. And this one is another cleaner approach which we saw originally, the recursive approach, right side view. And if the right side view, right side nodes dot size is equal to level, then I'm just adding it to the level. Otherwise, I'm taking the right side recursion first and then the left side recursion and incrementing the level and then passing on the right side nodes that resultant array. This makes sense. Yeah, let's move on to the next problem now. So that is range sum of BST. Range sum of BST. This is a LeetCode easy problem. Given the root node of a binary search tree and 2 integers, low and high, return the sum of values of all nodes within the value in the inclusive range low and high. Okay. Given the root node of the binary search tree and the 2 integers low and high, return the sum of values of all nodes within a value in the inclusive range low and high. Okay. Values are given. Low is 7 and high is 15. So all the nodes within low and high inclusive range. It's an inclusive range. So 7 and 15 are included. So 10, okay, 10 is inclusive. 5 is not included. 15, 10 plus 15 is 25. 25 plus 7, 32. 32 is the output here. 18 is above the range. 3 and 5 are below the range. And 7 and 15 are in the range since it is inclusive. So basically we just traverse through the tree. We do traverse the tree and then check the value if that is in the range and then add it to the sum. That's it. So if root is equal to null, return 0. Otherwise, current value is equal to root dot value is less than low or root dot value is greater than high. then 0. Current value is equal to root dot value is less than low, or root dot value is greater than high, then 0. Otherwise, it is root dot value, that is the current value. And then return current value plus range sum of root dot left, and then I'm passing the low comma high, and then the range sum of root dot right, which is low and high, whatever is returned in this one. So that would be added as well into the output of the original node or the root node. So yeah, this is times O of n and space complexity O of n. Since I'm recursing through each of the nodes, and in the worst case there can be n nodes in the stack. Okay, let's execute this one. Looks good. Let's move on to the next problem. K closest points to origin. Let's refresh this page to see how many we solved. Yesterday we had 20 problems, so we solved 7 problems now, so it made up to 27 now. Okay, K closest points to origin. Given an array of points where points of I is equal to xi and yi represents a point on the xy plane and an integer k. Return the k closest points to the origin 0, 0. Okay, the distance between 2 points on the xy plane is, in the Euclidean distance, square root of x1 minus x2 whole square plus y1 minus y2 whole square. You may return the answer in any order. The answer is guaranteed to be unique except the order that it is in. Okay. K closest point to the origin. Okay. So I have initialized the priority queue and I'm comparing here pair of integer array and integer. Why I have taken pair of integer array and integer here? So pair of integer array is basically the point, and then integer would be, I think, the distance. I think pair of integer array and the integer, yeah. So yeah, that would be the distance. Otherwise, what I could have done is pair of integer array, like just it could be priority queue of integer array with 3 elements. Zeroth element is x, first element is y, and second element could be the distance. That is another way, but here I think this keeps it neater, I guess, because the point is represented by an integer array of 0 and 1, so that makes it more clearer. Like, yeah, if we don't want to use a pair type, or if that is not supported in the language, in order to code it quickly, then just we can extend the integer array here. Instead of new pair, I will instantiate a new integer array and add points of I, points of 0, points of I of 0, points of I of 1, and distance as the 3 elements. Okay, so and how the distance is calculated, distance from the origin. Here also I'm comparing integer.compare pair.getValue, pair2.getValue, and pair1.getValue. That means what? That means what? Okay, integer.value, pair2.getValue. So the distance in the reverse sorted array. So this is a priority queue, which is a max heap, I guess. So k closest points to the origin. So we need to find k closest points to the origin. So we care about the minimum elements. So if something is at the farther distance, we don't want to keep that in the priority list. So we will keep the top k closest elements, or top k smallest distance elements. So top k smallest distance coordinate means, in order to keep top k smallest distance coordinate, it has to be a max heap. so that the worst element can be swapped out or compared with the P. So let's name it as max heap instead of just priority queue. Let's make it as max priority queue. At the least, that will make it clearer. Okay. Okay. And then get the distance from the origin. How the distance is got from the origin? Point, like we are just doing 0.0 star 0.0. So it is x square. Like here it's given x1 minus x2 whole square plus y1 minus y2 whole square. And it is said that we are caring about the distance from the origin. So the distance from the origin means origin is 0, 0. x1 minus x2 whole square means basically it is x1 square. x1 minus x2 is 0 means it is x1 square plus y1 square since y2 is also 0. x1 square plus y1 square. So x1 square is calculated by point of 0 star point of 0 plus point of 1 star point of 1. That's the distance from the origin. So we know the distance from the origin, and then we are adding it to the max priority queue to keep only the k closest element of k elements with the smallest distance from the origin. So new pair of points of I distance. Okay, if the max priority queue dot size is greater than k, then we are just polling it out. And then in k closest points is int of k comma 2, and then returning that those k closest points. Okay, int of k comma 2, k closest points of I is equal to max priority queue dot poll dot get key. Okay, it's almost as that top k elements, but in order to arrange it rather than the frequency, here we are calculating the distance from the origin, and it's a reverse distance since we are calculating the closest distance. That means the smallest values. Their top k elements is we were caring about the largest frequencies, here the smallest distances. So that's why max CPR. Okay, that's about this problem. Let's move on to the next one. Maximum swap. You are given an integer num. You can swap 2 digits at most once to get the maximum valued number. Return the maximum valued number you can get. Maximum swap, LeetCode 670 maximum swap. You are given an integer num. You can swap 2 digits at most once to get the maximum valued number. Return the maximum valued number. So in this one, let's see how we can go about this problem. So num, example 1, num is 2736, and then output is 7236. 2736. Return the maximum valued number that you can get. You can swap two digits at most once. At most once. Only once I can swap 2 digits. Okay, and that too only swapping. So instead of 2 and 7, I'm swapping 7 and 2. Okay. So basically, I think the logic is the largest elements that can be swapped at the largest position. Here 9973, the largest elements are already in the largest positions. So 73 are like, it's already the largest possible value, so no swap, and 9973 is the maximum value. Like with none of the swaps, this could have been made better. So we can traverse from left to right, and if we encounter any larger elements from left to right than what is in the, okay, basically it's simple. From the beginning position, we expect it to be the largest element. If it is not the largest element, swap it with the largest element. If this is the largest element, swap the next largest element with the next position, next largest element. So basically, I need to sort it in the reverse sorted order or the decreasing order, but only one swap is possible. Like it's just one part of the bubbles. Let's check how we can do this one. So let's convert it as a string instead of this one, just for the ease of operation. String num is equal to And I hope anything with 0 prefix value is not allowed. But let's see, I can add that as a test case and see. Okay, and then if just figure out the maximum element or maximum digit there. So first iteration I'll just use to figure out the max digit. Okay, it's not worth it if I figure out the max digit, and then if the max digits index is same as the uh, maximum value position, then it's not a ideal output. So what can I do? Okay, so I don't want to just determine the max digit, but I need to determine the position of the max digit here, or position of each digit here. So instead of I'll create a map of character, or maybe just an integer also, and then it's index, which is an integer, uh, digit index map. Okay, if I don't need any if here, digit index map dot put, so the current character is current digit is equal to string num dot char at I minus 0. Yeah, that would give the current digit. So current digit, if it already exists, then it's fine. So do I care about the first occurrence, or do I care about the last occurrence? So what do I care about most? So for each digit, I care about the last index because that is the most favorable to swap. I don't want to swap the leftmost element or leftmost digit only. So with one swap, I should hit the maximum goal. So let's see that. If current digit dot put, okay, current digit dot I. So even if it exists later, it gets replaced. So and then for every digit here, again I'll do the same logic. And then instead of making this a string num, let's make it as char array. That would be good to store. So that is to be char array. And then how else can we do this? How else can we go about it? String dot value of num char array. Okay, numbers to char array. And then, okay, this is the char array. Char array dot length. Char array of I. Okay, this is great. And here again, char array dot length. Okay, and then for every digit or every element, I need to see if the element which is greater than that exists. If that exists, then I'll just swap it with that. So for every element, current digit is this one and current index is I. So while int current index is equal to I. Okay, while current index is less than 10, not the current index, current digit. Int probable swap is equal to current digit plus 1. Okay, so probable swap and probable swap index I plus 1. Okay, so all I'll do here is for int I int j is equal to probable swap index j is equal to I plus 1. Let's make it as I plus 1 minus 1. Okay, or if it's equal to I, just keep it as I, and probable swap is equal to, okay, j is equal to I plus 1, j less than char array dot length j plus plus. Okay, and here if the char array dot char array of j is greater than char, if it's greater than the current digit, then that could be a probable swap. So then probable swap index would be equal to I, probable swap index will be equal to j, and then probable swap will be equal to current, not current digit, probable swap will be equal to char array at j. Okay, and then once I go through that for loop, if probable swap index is not equal to I, then basically swap I comma probable swap index in the char array, and then return char array dot toString. If none of these works, then just return num as it is. Okay, let's give it a try. Okay, string num dot caret I. This is not string num. Now we change it to char array. And yeah, I haven't implemented swap. Private static private void swap, and this would be char array. Char array and int I comma int j. Okay, here char array of char c char temp is equal to char array of I, and char array of routine swap method. Char array of j here. And then this would be replaced with temp. Okay, for input string something number format okay, string non-string is equal to okay, how to convert a char array to string in Java. New string of char array. Okay, understandable. So there was 7 here and then 6. Okay, I swapped 6 and 7, index of 6 and 7. Okay. I thought probable swap index will be greater than I. Okay, if the char array of j is greater than current digit. If it's greater than probable swap. Okay. If it's greater than probable swap, then I'm swapping, not if it's greater than the current digit. That would be true for the first greater element, but eventually I'll need to compare it with the probable swap. That's why I'm assigning this value here. And then what if it is a large string? Then this won't succeed. Let me submit it. It will fail for a large string of large length or big one. So first thing is 1.0. This itself failed 1.0 10, and I'm giving the output as 1 because why? Why did I truncate it? Okay, did I make it as 0 1? I might have made it as 0 1. Let me see. Okay, I have made 1 0 as 0 1, and that's why it's returning 1. So why 1 0 became 0 1? Let's see. 0th index, I came here. The current digit is 0, that is 1. Okay, current digit is 1, and I'm looking for the next probable swap in these things. If the probable swap index, the probable swap index is I, and the current digit is current digit. Okay, whatever the current digit is. If the probable, so I'm coming here, j is equal to I plus 1. If j is less than char array dot length and j plus plus. If char array of j is greater than probable sweep. Okay, swap of char array of I, probable swap index. Probable swap index is how how it became this one. Let's use the debugger in the interest of time. Okay, so for 1 0, now the current digit is 0, and the current index is 0, and the current digit will become 1. And then probable swap index is I, which is 0. Probable swap is current digit, which is 1, and j is equal to I plus 1, which should be 1. Okay, if char array of j is greater than probable swap, char array of j is greater than probable swap, no. char array of j, char array of 1, char array of 1 is greater than probable swap. Okay, I'm comparing the character with the integer value here, that's why. So what can I do here is, if char array of j minus 0 is greater than probable swap. So yeah. So here another case, 98368, 98368, 98638. Expected is 98863. So 8 and 3 had to be swapped. What I did was I swapped 6 and 3. Why? Why didn't I consider the last case? So let's look into that one as well. So first couple of rounds are current digit is 9. There is nothing greater than 9. Let's keep going. And then yeah, there's nothing. So current digit is again 8. Here current digit is 8. There's nothing greater than 8 again. So not interested. And here probable index is equal to I, so nothing happens. And next element here, current digit is 3. Now there should be a probable swap. Probable swap is okay. It is greater than that, the next element. So probable swap index is 3. Probable swap index became 3. And then probable swap is 6. Probable swap is equal to char array of j. So that should be okay, minus 0. So probable swap is equal to, this 2 should be equal to minus 0. Equal to current digit basically, yeah. Current digit and char array of j minus 0. Current swap, current comparable, int current comparable is equal to, okay. So I'm comparing character and digit everywhere. Okay. So here, now I'm giving the right output 98863. So let's execute it. For a large output or the large number, it should still timeout. Okay, 9193. Okay, 9913. Again, what's wrong? Let's see. Okay, current digit 9, so not significant. There is nothing. Okay, 9913 and 9. Okay, 1993 is the number given. I should replace it with this 9 should replace this 1. What I did is I replaced this 1 with this 9. So I should replace it with the rightmost 9, not the leftmost 9. So all I can do is, if the probable swap index or the current probable is greater than or equal to also. If it is greater than or equal to this, then I will do that. Okay. How is that impacted if I change this? 993. And then if I make it as greater than or equal to probable swap, okay, 98368. Okay, for 9 there is nothing. And then for 8 there should be nothing again. Oh, oh, I compared it with this one, and then if it is greater than or equal, then I'm just swapping it and doing nothing. It's returning the same value. 98368 would return 98368. So how should we go about it? Let's start with the next element itself rather than having the current element. If the probable swap index is -1 and probable swap is integer dot min value. Okay, and if probable swap index is not equal to -1, then I will run this. Okay, here maybe I can just have it as current digit. Again, it would be the same problem, greater than or equal to the current digit. What I can do is, yeah, greater than or equal to the current digit. +1. Okay, it gave me the solution, working solution. What I did is I didn't compare with the current value. If I compare it with the current value, even if there is the same value, then I end up considering that as a swappable and used to swap it. So now I just made it as +1, and then if the probable swap index is not equal to -1, then I'm swapping it. So if I remove this print statement, then that should improve the time a little bit. Yeah, it helped the time a little bit only. Another thing I'm missing here is for a really large number, for the really large numbers, I can make use of this hash map, digit index map, and which I'm not doing. So what I can do is okay, I can just like it's basically I can do like 9 comparisons. There are 9 digits or 10 comparisons, 0 to 9. So 10 comparisons. I won't compare 0. So 9 comparisons for every number. So that would be constant runtime only. And Okay, instead of this looping through each of the numbers and trying to find it again and again, this is like a repeated computation, which I have done here. So what I can do is, let's do while, okay, int num is equal to 9, and while num or int probable swap is equal to 9, and while the probable swap is greater than the current digit. I'll keep looking for the probable swap, and then I'll subtract the probable swap by -1. Okay, I'm keep subtracting it, and here when I'll think of swapping, if my index map contains this one, if digit index map dot contains key for the probable swap, and digit index map dot get probable swap is greater than the current index, which is I, is greater than I, then just swap it. Okay, then just swap it, and then just swap I with the probable swap index. Probable swap index is got by digit index map dot get. Okay, swapping with this index, and then once I swap this one, I need to break out of that loop, and I don't need this thing anymore. Integer dot value of string of array. Okay, I don't need these things as well. Two 736. Okay, it has done more than one swaps here. 7 6 2, 3. Okay, I'm still within the for loop. So rather than doing that, I can just return this one there. Okay. So the logic behind here is I have converted my string to char array, string dot value of num. Okay, let me see if there is a way to convert string to integer to char array and vice versa. In Java. String dot value of number and then converting it to char array, and then again here integer dot parse of string new string of char array. I think we are doing the same thing. So there are two steps involved. Char array we need to convert it into string and then convert it into integer. And same way, integer we need to convert to string and then we need to convert it to char array. Okay. So let me just brief it out. Char array, I converted the given number to char array, and then I created a digit index map where I map the index of the digits based on that char array position. Like for each digit, what is the last index in that char array? So I took that. Basically, it's overriding it if I find it on the rightmost side even more. Current digit is equal to this one. Okay. Or we can just do this. Since we are using it only once. And for int I is equal to 0, I less than char array dot length I plus plus current digit is equal to current char array of I minus 0. Okay. And probable swap is I'm starting with 9. While probable swap is greater than current digit, if it is greater than current digit, then I'll keep going. Like if the current digit itself is 9, then I won't bother doing anything. I don't want to swap it with anything. If the current digit is 8, then I'll check if there is a 9 on its right in order to swap. But if there is no 9, then I will just exit it. Okay, let's see. If current digit probable swap, I'm starting with 9. Okay, if the probable swap is greater than current digit, yes. And if it is contained in the digit index map, and also if it's on the, here I'm making sure if it's on the right side of the current digit, it should not be on the left side of the current digit, then I'm swapping it and then returning the value once I swap it. There's only one swap allowed. So yeah, basically that's the whole logic. Let's see the editorial solution if there is anything better or similar. Open square, we're not interested. Greedy 2-pass. Approach 1 is inefficient because not all swaps are worth making. Let's consider an approach where we focus only on the swaps that will give us the biggest improvement. Can we identify a pattern in the results that will help us identify the best swap? If we think through some examples, it can be observed that in each example, the optimal swap involves moving the largest digit we can move forward to replace a smaller one. To achieve this, we make 2 passes over the number. In the first pass, we scan from the right to left to identify and store the largest digit we find and its position. In the second pass, we move from left to right. Now that we know for each position the largest digit that appears after it, we check if we can make a swap. The first time we find a digit that is smaller than the largest one that comes after it, we swap them. Since we are always looking for the largest possible swap, this guarantees that we will maximize the number. Okay, convert the integer to string. Determine the length of the string. Initialize the array max write index of size n to store the index of the largest digit from the current position to the end of the string. Populate the max write index in a single backward pass. Set max write index of n-1 to n-1. Okay. Iterate from the second last digit to the beginning of the string. If the current digit is greater than the digit at the index, okay, in the last pass, okay, got it. So here they have the max write index from the current index, so they have come from the right and then storing this one, and then max write index, okay, new integer of max write index of n-1 is equal to n-1. Okay, this seems like a good approach as well. Let me try to rewrite this method once. So I'll try to explain it while I code it. Basically, so I stored it in a hash map, but they are storing it in an integer array. And also they have the information about the maximum value on the right side of the array. That's a good strategy to come from the right side and then think about what is the maximum value on its right. So integer array max right value is equal to new int of char array dot length. Okay, so here I don't need a digit index map, but I'll just keep it for now. But I would need something like int max till now integer dot min value max till now is, I'll keep it as -1. And then also here arrays dot fill. Okay, and max till now is -1. Max write values is equal to max till now, and if max dot max of max till now comma char array of I -0. So that is the max till now. Okay, and now while iterating through each of the digit here, if the max till now is greater than the current digit, Okay, I need to store the index of it rather than max till now. Okay, so what I'll do is if max till now is less than the current char, if it is less than current digit, max write index. Max write index also is -1, then max write index will become I. Max write indexes. Okay. Max value here. Okay. And max write index. And also I need to assign max value equal to current digit. Okay. So now I'm going through one more pass, and current digit is this one, and okay, and then I'm checking if max write indexes is greater than I, then need to swap char array comma I comma max write indexes of I. And once we swap it, we can just return it. Max write values is equal to max write value plus I is equal to max write index. No, not max write values, it is max write indexes. Okay, 2736. Why is it the case? Let's see. Oh, int is equal to, I need to traverse backwards. And then if I is greater than or equal to 0. Okay, 98368, 98368. Let's see what's wrong with this. So max right index is 0, 1, 2, 3, 4, already 4 here, and then 4 for this, for that one as well, and then 4 for the other one as well. Okay, here okay, here it is less than or equal to current digit. Same problem that we got the other time. 9193. First time when we encounter this. Okay, we need to swap it with the last letter. 9913 it should be. Okay, let's not do this quality check here. If it is less than this, then I'll do this. So I need the rightmost values. But here, in order to swap, if max right indexes is greater than this one, and also max right values, like value at that index, and max right index is equal to this. Max right value is equal to char array. Okay, this is max right value. So if max right index is greater than I and max right value is greater than current digit, then only swap, otherwise don't. Okay, let's submit this. Okay, anyway, runtime did not, oh, it did improve. Am I printing something? Yeah, there is some error. So it came 100% once. Yeah, it's close to the best performance now. So yeah, evidently from this one, do I need this array start fill? I don't think so. So I just remove this one, and yeah, this is a bit tricky. Here I need to just remember that digit index map is equal to new hash map, and max value is equal to -1, max right index is -1. and char array dot length I greater than I. Okay, from the right I'm coming and filling the values. Max right index is okay. If it is max right index and max right values, I'm filling the right way. And then here before swapping, I need to check if it is the same value or not. Even if it's the greatest number on the right, or the max right index is on the right side, if the value is also greater than or not, I need to check that and then make sure it works. So I think that's about it. We were able to solve 9 problems in the session, so that's good. And I appreciate whoever is watching. I see message from Chandu Pulpaka. Hey bro, how are you? Welcome to my live stream. Let me know if you have any problems or if you want to learn about anything or if you have any questions about the approach that I'm following here. I'm happy to schedule some time and help you with your preparation or your learning journey. Yeah, keep me posted. Thank you, and have a good time. I might do a live stream once again in the evening today or maybe in the morning. Have a good one. Bye.